imagine you're trying to read a really gripping mystery novel.
Yeah.
But there is a massive catch.
Okay, I'm listening.
You are only allowed to read left to right, one single word at a time. And you can never, under any circumstances, let your eyes dart backward to double-check a clue.
That sounds incredibly frustrating.
It is. I mean, the detective announces, the butler did it. But you cannot look back to see what it actually was 3 paragraphs ago.
Yeah.
You just have to guess based purely on what comes next.
Right.
That crippling limitation, that total inability to look backward or process a whole sentence at once, is exactly how artificial intelligence read text before October 2018.
It really was. I mean, it was a severe structural handicap for the entire field of natural language processing.
Welcome to the deep dive, by the way. We're settling in for a deeply curious, immersive conversation tonight.
Custom tailored for you, the listener.
Exactly. Especially if you're a software engineer trying to map out the rapidly shifting terrain of AI architectures. Our mission today is to explore the source material detailing the history and the mechanics of BERT.
Bidirectional encoder representations from transformers.
That's the one. We're going to unpack how this specific model fundamentally altered the developer landscape, creating the modern paradigm we live in today, the great divide between the readers and the writers in AI.
And to understand the magnitude of that shift, we first really have to look at the mechanical reality of those early left-to-right models. Up until BERT, the dominant engineering approach was strict left-to-right language modeling.
Like GPT-1.
Yeah.
Right, which actually launched just a few months before this breakthrough.
Exactly. Engineers were building models that functioned just like your mystery novel scenario. They predicted the next word based exclusively on the sequence of previous words.
Because in neural network architecture, reading strictly left to right requires something called causal masking.
Yes, causal masking.
Let's break that down for someone who, might be building applications but hasn't necessarily dug into the underlying matrix math. Causal masking is essentially a mathematical blindfold, right?
That is a really highly accurate way to visualize it. When you feed text into a model during training, you represent that text as a massive grid of numbers.
Right, the matrices.
Yeah, and if you want the model to learn how to predict the next word, you can't let it see the future. So causal masking literally zeroes out all the future tokens in the matrix.
So when the model looks at word number 4,
the math physically prevents it from attending to word number 5 or 6.
Let's apply that to a really practical example from our source material. Take the sentence. He walked along the riverbank on a sunny day.
A classic NLP example.
Right. So if you're a strict left-to-right model with a causal mask, you process, he walked along the river, and then you hit the word bank, and you're essentially stuck.
Completely isolated from the future context.
Exactly. The mathematical representation of bank is just sitting there. You don't know if the guy is going to deposit a check or if he's feeding ducks. You desperately need the words sunny day to disambiguate the context.
But the causal mask ensures the model hasn't seen sunny day yet.
And the early AI community knew this was a massive problem, didn't they?
Oh, absolutely. The state-of-the-art model right before BERT was called ELMo, and the engineers behind ELMo attempted to fix this lack of forward context.
But the architectural solution they landed on was a bit of a crude hack.
You could say that. They used concatenation. So they trained one completely independent model to read left to right.
Okay.
Then they trained a second, entirely separate model to read right to left. Once both were trained, the system simply mashed their mathematical representations together at the very end.
Right. But the crucial flaw there is that the left reading model and the right reading model never actually interacted, right? Like they didn't share information during the deep processing layers.
Exactly. They were entirely siloed until the output.
It sounds like having two one-eyed people describing a painting from opposite sides of the room. And you, as the engineer, are just trying to stitch their conflicting descriptions together into one coherent image.
That's a great way to put it. They aren't actually perceiving depth, they're just yelling their half perspectives at you from across the room. The representation was incredibly shallow.
Which brings us to Google.
Right. This is where the researchers at Google introduced the architectural elegance of BERT. They asked a fundamental question. What if we just open both eyes?
Wow.
What if the neural network could look in both directions simultaneously at every single layer of processing?
So they built a transformer encoder stack, but they stripped out the decoder And more importantly, they completely removed the causal masking.
Removing that blindfold was the key. An encoder stack is essentially a series of layers where every token looks at every other token to figure out how they relate to one another.
So by removing the causal mask, they allowed full bidirectional self-attention.
Yes. From the very first layer of the neural network all the way to the last, the context is deeply fused.
So when BERT encounters the word bank, in our previous example,
Its internal mathematical representation of that word is immediately and simultaneously informed by both river before it and sunny day after it.
that's huge. And the sources mentioned the original release included 2 sizes to give developers options. I know the base model was 110 million parameters. Do you have the numbers for the larger version?
BERT large was 340 million parameters.
Which is funny because if you're working with today's open source models, those numbers sound incredibly quaint. I mean, the largest variant of Llama 2 is 70 billion parameters, and frontier models are pushing well past 1 trillion.
Yeah, they are microscopic by modern standards. However, in 2018, training a dense 340 million parameter model was a massive computational undertaking. It pushed the absolute boundaries of what the industry considered feasible.
But here's where the narrative hits a wall for me. If you put your software engineer hat on and look at a system with full bidirectional attention and 0 causal masking, you immediately spot a massive fatal vulnerability in the training loop.
The training paradox.
Right. If BERT can see the entire sentence at once, how do you train it to learn anything? Because traditional language models learn by predicting the next word, right? And then calculating the error when they guess wrong.
Exactly.
But if BERT has no blindfold, it can simply look ahead. If I am training the model to predict the word at position 5, and it has full bidirectional attention, it can literally just look at the answer key at position 5.
You would absolutely cheat.
The loss function drops to 0 immediately, the error is 0, and the neural network learns absolutely nothing about language. So how do they solve that?
The Google researchers solved this paradox with an ingenious mechanism called masked language modeling.
Usually abbreviated as MLM, right?
Right, MLM. If the model can't predict the next word because it can already see the whole sequence, you have to fundamentally change the game.
Yeah.
You transform the training objective into a fill-in-the-blank puzzle.
Like the blank sat on the mat, guess the blank.
That is the exact mechanism. During the pre-training phase, the system randomly selects 15% of the tokens in the input sequence.
Right.
The model is then forced to process the entire sequence and predict what those hidden tokens originally were, relying entirely on the deep bidirectional context surrounding the blank space.
Now, our sources detail a very specific breakdown for how that 15% is handled, and this is where I get a bit stuck on the logic.
The 80-10 split.
Yeah. So of the tokens selected to be masked, the engineers replace 80% of them with an actual artificial mask token.
Correct.
But then 10% are replaced with a totally random word from the dictionary. And the final 10% are left completely unchanged, even though they were ostensibly, selected for masking.
Right.
Why introduce that level of convolution? I mean, why not just mask 100% of the selected tokens with the artificial mask tag and streamline the code?
It comes down to anticipating edge cases in production. See, the mask token is a purely artificial training construct.
Yeah.
When a developer downloads BERT and deploys it in the real world to, say, classify a massive database of emails or analyze legal documents, the real-world text will never contain a mask token.
Oh, I see. So if the neural network only ever learned to engage its deep contextual reasoning when it was explicitly triggered by a mask flag,
It would fail catastrophically in production. There would be a severe mismatch between the pre-training environment and the real-world fine-tuning environment.
that makes sense. So keeping the original token 10% of the time solves that mismatch.
Exactly. It teaches the model that it cannot blindly rely on the visual cue of a mask token to do its job. It has to constantly evaluate the context to ensure the word that is already there actually belongs there.
Okay, I understand leaving the original word, but what about throwing in a completely random incorrect word from the dictionary 10% of the time? That feels like you're gaslighting the AI. You are deliberately feeding it bad data.
It is a form of productive gaslighting.
Productive gaslighting. I like that.
Throwing in random tokens forces the network to become highly skeptical.
Yeah.
It constantly has to verify its own understanding of the sentence. It can never just trust the input sequence because any given word could be an imposter.
Wow.
This architectural choice forces BERT to maintain a highly robust, deep mathematical representation of every single token in the sentence, rather than only focusing its computational power on the obvious blanks.
It's essentially defensive programming applied directly to neural network training objectives.
That's a perfect analogy.
So BERT is successfully trained, it can read in both directions, it understands deep context, and it doesn't cheat. Reading through our sources, the launch of this model didn't just advance the academic science, it completely democratized AI for everyday software engineers.
Oh, the release of BERT triggered a massive framework shift in how developers approached machine learning.
Because before BERT, if you wanted to build a natural language processing application, let's say a custom sentiment analyzer, for your company's product reviews, you had to build a custom neural network architecture entirely from scratch.
Yes, you needed to amass a massive labeled data set specifically tailored for sentiment analysis, and you had to train the entire system from the ground up.
Our sources use a fantastic analogy for this, the polyglot analogy. Building from scratch before BERT was like trying to teach a newborn baby the intricate rules of a highly specific card game.
Which is nearly impossible.
Right. You have to teach them what cards are, what numbers mean, and how humans interact, all while trying to teach them poker.
Whereas pre-training a model like BERT is akin to raising a genius polyglot who has already read millions of books and understands everything about global syntax, grammar, idioms, and general world facts.
And fine-tuning that model is simply pulling the polyglot aside and saying, here are the rules to poker.
Exactly. They already possess the foundational knowledge of language, so teaching them the specific rules of a new task takes a fraction of the time and data.
Do we have the hardware numbers on what it cost to raise that polyglot originally?
We do. Google utilized 64 of their proprietary TPU chips, running continuously for 4 days.
4 days.
Yeah. They trained the model on 3.3 billion words, which was essentially the entirety of the English Wikipedia and the Toronto Book Corpus.
That represents an incredibly expensive, computationally heavy pre-training phase.
Absolutely. But the pivotal moment was when Google decided to open source those pre-trained weights.
Which meant a computer science grad student with a standard single laptop GPU could download the Genius Polyglot for free.
Yep. They could add one simple linear classification layer on top of the architecture and fine-tune it for their specific sentiment analysis task in a matter of hours rather than weeks.
And the benchmark results from this new workflow sent shockwaves through the industry. I mean, the GLUE benchmark, which is a massive standardized collection of diverse language understanding tasks, jumped from a previous state-of-the-art score of 69 all the way up to 80.
And on the Squad 1.1 reading comprehension dataset, BERT achieved a score of 93.2.
While the human baseline performance on that exact same test is 91.2. A machine learning model literally beat humans at reading comprehension for the first time.
That milestone is why, almost overnight, the era of building task-specific architectures from scratch ended. The pre-train then fine-tune paradigm became the absolute, unquestioned default for the entire software engineering field.
Okay, so this brings us to a major pivot point. BERT crushes the global benchmarks, democratizes the engineering workflow, and proves open-source weights are the future. If it was such an unprecedented success, why isn't BERT the engine behind the massive generative chatbots we interact with every single day?
This hits on a fundamental trade-off in systems architecture. The harsh engineering reality is that BERT is an unparalleled reader, but it is a terrible writer.
The generative wall.
Exactly. We established that BERT derives its power from full bidirectional attention. That is its superpower for deep contextual understanding. However, to generate text, to write a coherent response to a user's prompt model, must output text one token at a time in sequence.
Autoregressive generation.
Right.
Generating word by word, moving strictly left to right.
And autoregressive generation strictly requires causal masking. You cannot allow the model to look ahead at the future context if the future words haven't been generated yet.
Of course.
BERT's entire foundational design was built to break free of that left-to-right constraint. When you attempt to force BERT to generate text, it fundamentally lacks the internal architecture to do it efficiently.
There is a research paper cited in our sources with an incredible title. BERT has a mouth, and it must speak.
I love that paper. It's a fascinating case study of engineers refusing to accept an architectural limitation.
The methodology is agonizing to read about. To make BERT write a sentence, you have to feed it an artificial mask, run a massive forward pass of the entire 340 million parameter model just to predict that one single word.
Just one word.
When you lock that word in, add another mask to the sequence, and run the entire model again from scratch. The computational overhead is staggering.
The output is incredibly slow, the text feels clunky, and completely lacks the fluid natural generation speed of a GPT-style decoder model.
That experiment perfectly illustrates the modern divide, doesn't it?
Yeah.
Encoders are optimized for understanding deep context. Decoders are optimized for sequential generation.
Precisely. But before the industry fully pivoted to scaling up massive decoder models for chatbots, the open source engineering community spent several years furiously trying to perfect and optimize the BERT encoder recipe.
Right, which spawned an entire family tree of optimized models. Let's briefly run through the family tree showing how the community optimized the recipe, because I see these names constantly in GitHub repositories.
Sure. Well, pretty early on, there was Roberta, which basically proved that the original BERT was severely undertrained. They trained it longer, with bigger batches, and actually dropped the next sentence prediction task entirely.
Oh, nice. And then there was the size and efficiency problem. The original BERT was bulky.
Right, so Google released Albert, which solved the bloat by introducing parameter sharing across all the neural network layers. They realized a significant portion of BERT's parameters were actually redundant.
They were just doing the same mathematical work.
Exactly. So by sharing those parameters, they drastically shrank the memory footprint while maintaining performance.
And then Hugging Face tackled efficiency with DistillBERT. They utilized a technique called knowledge distillation.
The teacher-student paradigm.
Right. For a software engineer, you take the massive, fully trained BERT model, the teacher, and you use it to train a much smaller, leaner student model. The student doesn't learn from the raw data. It learns to mimic the final mathematical outputs of the teacher.
And DistillBERT retained 97% of the original performance, but ran twice as fast, which made it heavily adopted for mobile and edge computing environments.
But there were other bottlenecks too, like spatial reasoning.
Yes, Microsoft introduced DiBERTA to solve this by introducing disentangled attention.
Disentangled attention.
Yeah. In the original BERT architecture, the mathematical information about what a word means and where that word is positioned in the sentence are mashed together very early in the processing layers.
It's like working on a massive jigsaw puzzle, and standard BERT tries to memorize what the puzzle piece looks like and where it belongs on the board simultaneously.
Perfect analogy. DiBERTA disentangles that process, giving the model one distinct map for the meaning of the word and a completely separate map for its location in the sequence.
And then combines them later.
Exactly, resulting in vastly sharper spatial reasoning.
And then the final major optimization we should touch on addressed training waste. The original 15% masking rule meant that 85% of the sentence was essentially ignored during the error calculation of any given training pass.
Right. A model called Electra solved this inefficiency by throwing out the mask token entirely. Instead, they used a small generator network to quietly swap in highly plausible fake words.
So the main model acted as a discriminator.
Forced to play detective on every single word in the sentence, constantly asking, is this word real or is it a fake? This forced the model to learn from 100% of the tokens on every pass,
drastically reducing the compute time required to reach state-of-the-art performance. So all of these descendant models optimized the reader, but none of them could cross that generative wall.
Right.
Eventually, the scaling revolution took over. Models like GPT-3 proved that if you make a left-to-right decoder massively huge, it develops the ability to do complex understanding tasks through pure scale,
bypassing the need for task-specific sign-tuning entirely, which leads to a critical evaluation of where we stand today. With trillion-parameter decoder models dominating the cultural conversation, it is easy to assume BERT is just a historical footnote.
But looking at the actual systems software engineers are building and deploying in enterprise environments today, BERT is very clearly not dead. It is quietly running the back end of almost everything.
Oh, absolutely. BERT found its permanent, highly lucrative niche as the ultimate workhorse for classification and understanding tasks at scale.
Give us an example.
Consider an enterprise system that needs to route millions of incoming customer support tickets or detect spam in a global email network. Booting up a 70 billion parameter generative model to perform a simple binary spam or not spam classification on a million emails is financially ruinous.
The compute costs would bankrupt a startup before the end of the month.
Literally. But a highly optimized, fine-tuned BERT model, sitting at perhaps 100 million parameters, can process those millions of emails with incredible accuracy at lightning speed for pennies on the dollar.
There is another massive modern application we need to bridge here. If you are an engineer building AI tools right now, there's a very high probability You are architecting a RAG system retrieval augmented generation.
Yes.
You take a user's complex query, search your company's proprietary database for the relevant documents, and then feed those documents to a massive generative model to write the final eloquent answer.
And the engine powering that crucial initial retrieval step is almost always a BERT-derived model.
This is where we need to connect the dots on how a fill-in-the-blank game became a search engine. When a BERT model processes a sentence, just before it guesses the blank word, it converts the entire contextual meaning of that sentence into a vector embedding.
And for the developers listening, an embedding is just a massive array of numbers. It maps the meaning of the sentence into a high-dimensional physical space.
So in that mathematical space, sentences with similar meanings are located physically close to one another, regardless of whether they use the exact same vocabulary.
Precisely. So engineers realized they could take a pre-trained BERT, chop off the final classification head that guesses the blank words, and just use the underlying vector math.
Frameworks like SentenceBERT do exactly this.
Yes, they do.
When a user types a highly nuanced query into a RAG system, SentenceBERT reads the query in both directions, understands the deep semantic intent, generates the vector embedding, and retrieves the matching documents from the database in a fraction of a second.
The massive generative model gets all the credit for the eloquent conversational response presented to the user, but it is the BERT encoder in the basement doing the actual heavy lifting of semantic understanding and retrieval.
The decoders are the charismatic front-end writers. The encoders are the brilliant, hyper-fast librarians in the back room. I love that.
It's a great partnership.
So to summarize the technical journey we've mapped out today, BERT fundamentally shifted the paradigm by opening both of AI's eyes. It proved that massive, unsupervised pre-training reading in both directions with a transformer encoder and no causal mask could create a highly versatile, general-purpose language engine.
It transformed the entire developer workflow from build everything from scratch to download the polyglot and fine-tune.
And it permanently established the baseline truth that deep contextual understanding absolutely requires bidirectional attention.
Definitely.
I want to leave you with a final provocative thought to chew on today, drawn directly from the implications of our source material. The monumental success of BERT proved that the right training objective can matter just as much as raw scale.
Yes, an ingenious, playful, algorithmic design-masked language modeling, which is literally just an elementary school fill-in-the-blank game, allowed a tiny 340 million parameter model to completely shatter global performance benchmarks and beat human baselines.
It was a triumph of clever algorithmic design over sheer brute force computation. So here's the question for anyone building in this space. In our current industry, rush to blindly scale up left-to-right next word predictors to trillions and trillions of parameters. What clever, human-like learning objectives are we completely overlooking?
It's a great question.
We're currently missing the next fill-in-the-blank trick, the kind of architectural elegance that could spark the next massive AI revolution on a fraction of the compute power we are using today. Something to think about.